So let us start photoelectric effect today's class, and we'll try to wind up this topic. Okay, photoelectric effect. Photoelectric effect. PEE. Photoelectric effect. So what happens in this photoelectric effect is based on particle nature of light. Okay, and this phenomena was first explained by Einstein, and Einstein, gave the detailed theory about this, and he gave the postulates, and based on this, he was also given the Nobel Prize for this. He also gave the space, general theory of relativity and special theory of relativity, but nobody believed Einstein. Nobody believed him. Whatever theory he gave on, nobody believed him. Till date, also people find difficult to believe Einstein's theory because that is a complete contradiction of the classical theory. Okay, Newton's mechanics and all that. But still, many places they have done experiment and they found that the theory of relativity is valid. But it is looking like a fiction, like science fiction, so people don't believe it. But it is true, okay? Because something is there which we may not believe it, but it is there, right? Because light itself is an amazing thing because we do not know what happens when an object goes at the speed of light. Okay, but Einstein was fascinated with light from the childhood itself. He was thinking about it, and then he became more mature and he gave that theory of relativity. But anyway, that is not in our syllabus. We have to discuss about photoelectric effect. So let us start photoelectric effect. First, brief theoretical points I will give. I will write important notes of this. Okay, and then I will also explain the parallel. What are the important points that Einstein has given. Okay, so let us start with that. So first we need to note about electron emission. Electron emission. Electron emission. Okay. So we all knows that metals have free electrons. Metals have free electrons. Metals have free electrons, and these electrons, these electrons, these electron cannot escape out of metal surface. Metals have free electrons, but they cannot escape because they are bound with the nucleus. Okay. Now, the free electrons, yeah, the free electrons are held inside inside the metal inside the metal surface by attractive forces of the ion. Attractive forces of the ion. Now, if you want these electrons to come out of surface, you have to give some minimum energy. Okay, so a certain minimum amount of energy is required to pull the electrons out of metal surface metal surface out of metal surface, and this energy and this minimum energy is called work function, of the metal. Okay. So this is called work function. So what is work function? It is similar to the idea of ionization energy. Suppose on the surface of metal, but of course ionization energy is something which is like for an isolated atom. Suppose you take an atom and you want to kick out the electrons from the outermost shell, which is called valence shell, right? So if you want that electron atom should lose electron, you have to give some energy, right? That is called ionization energy in chemistry. But here in physics, this is not exactly ionization energy because electrons are present on the surface of the metal. So the electrons are of course free. It is a solid state. So electrons are loosely bound and electrons are free. And if you want the electrons to come out of the surface, you have to give minimum energy. That is called work function. So this work function has similar idea of ionization, but it is not exactly the same. Okay, right? So that's called work function. And of course, work function will be different for different metals. That is what we have to know. Suppose if you take, we are talking of metals only. So that means if you take any type of metals, some metals which are like very strongly bounding in free electrons, then it is more energy required. But some atoms or some solid, metals where the electrons are outermost shell, then it can easily lose. So depending on the nature. So now I am giving the values of work function. We should note that. We don't have to remember, but some rough idea we should have. Okay, that's why these theories are important to write. Okay, so work function, if you take work function is denoted by the symbol phi. Okay, and this work function is going to be 6.35 electron volt. Okay, this is the highest. This is highest value, highest for platinum, for platinum, highest for platinum, and this work function is lowest is 2.14 electron volt. This is lowest for cesium, lowest for cesium. These are metals, I think, right? Now I will make a table of this. So let us note that for different metal, work function in electron volt, then of course we can keep on writing for different metals. Okay, let us write this different value. If I take, for example, cesium, then potassium, then sodium, then calcium, manganese oxide, lead, right? Let us try to note down the values for this first. This cesium 1.14, right, minimum value, then 2.30, then 2.75, it is increasing, then 3.20, then 4.17, then 4.25, then uh, next is for aluminum, aluminum, mercury, He, copper, gold, nickel, and at last platinum, Pt. Yes. What are the values? Let us write it. So for aluminum it is 4.28, then 4.49 for mercury, 4.65 for copper, 4.70 for gold, sorry, silver, no, silver, no, gold or silver, Ag. I think Ag is silver, not gold. Um, and nickel is 5.15, and 6.35 highest for platinum, 6.35. Okay, so these values, okay, we don't have to remember, but we can understand something about, because generally they give in the questions in it, hopefully they give the values, or at least some idea they will give. We cannot remember all these things, these are information, right? So but one idea we should have, that cesium, if you take cesium has the smallest value of work function, smallest 2.14. And if you go here, highest is for platinum, 6.35. You can compare sodium, calcium, manganese oxide, lead, aluminum, mercury, copper. So like that. Copper is also in the highest side only, nickel, platinum, heavier things. Okay. So anyway, they have more work function, means they require more energy to eject the electrons. To eject electrons, they require more energy, right? Okay. Then now the minimum energy required to eject electrons can be supplied by. How can we supply the minimum energy? The minimum energy, the minimum energy required to eject electrons can be supplied by, different methods are there. How can we supply the minimum energy? And photoelectric is one of the method. Okay, the first method is thermionic emission. Therm, thermionic emission. Another is field emission. Field emission. Another is photoelectric. Photoelectric emission. So let us understand briefly and then going more detail into photoelectric emission. So thermionation means you have to give thermal energy by heating. By heating, by heating you can give energy. Field emission means by applying very strong field. By applying strong electric field. Strong electric field. How much is strong? Almost of the order of billion volt per meter. And this by irradiating the metal surface, irradiating the metal surface with suitable electromagnetic radiation or electromagnetic wave. Okay, so that is what we are going to study, photoelectric emission. So how can we eject the electron from surface of metal? By heating the metal, by applying a strong electric field, and by applying or by allowing the electromagnetic radiation to fall on the surface. And this is what is photoelectric effect that we are going to study. So let us start photoelectric effect in more detail. So first thing is that, what is photoelectric effect? Photoelectric effect, which first point we are going to see about the Hertz observation. Hertz observation. The scientist named Hertz, he observed about photoelectric effect. And what did he observe? Let us write in detail. So photoelectric effect, PEE, we are calling photoelectric effect as PEE. Photoelectric effect was discovered by Hertz. Hertz. in 1887. It was discovered in 1887 near to the end of the decade, 19th century. So what happens in that? What did he observe? He did some experiment. So Hart observed observed that high high voltage spark passes across the metal electrodes across the metal electrodes more easily more easily when cathode is illuminated with ultraviolet ultraviolet rays ultraviolet rays from an arc lamp. This is was the experimental observation by Hertz. Okay. So what does this mean? I will explain this. Hertz observed that high voltage spark pass across the metal electrodes more easily when cathode is illuminated with ultraviolet. Note that this is a radiation ultraviolet rays from an arc lamp. Arc lamp is a source of lamp. Let me explain what it is. Suppose that this is a metal which is called cathode. Okay, and how do you observe that high voltage spark passes across the metal electrodes more easily? So in metal electrodes mean there are two types of metal. One is called cathode and is called anode. And in between them, we apply a very strong battery. Let us say a very strong battery. And note that this space is completely empty. Okay? Space between anode and cathode is completely empty, but it's completely vacuum. Vacuum is there. Okay. So now, if we are producing electric spark means, first of all, it is very difficult to create an electric spark between them because maybe some gases or some molecules may be there. I think if you have studied cathode ray experiment, you may be knowing about it. This is like a cathode ray tube. Okay, cathode ray tube. What is cathode ray tube? CRT. This is called CRT, cathode ray tube. So what happens in cathode ray tube? Almost it is vacuum, and this is very high electric field is trying to produce between this, and the spark will be generated because some gases atoms may be there, and these gases atom will break down because of very high electric field. But high electric field, how to establish between them? So what happens here is that it is very difficult, but if you apply some ultraviolet rays, UV rays, then what happens is that electrons are lost from the surface of this, and as soon as electrons are lost, these electrons can travel between them, and as these electrons can travel, there will be current, and this is what we are talking about. Spark here means high voltage spark means we are talking about current. So current will be developed between them easily if you apply electromagnetic waves. Suitable electromagnetic means ultraviolet rays. Ultraviolet rays can eject electrons from this cathode, and these electrons can travel between the two plates. One of the plate is called cathode, another is called anode. So between these two metal plates, current can flow easily if you apply ultraviolet rays. Remember, this is almost vacuum only. You may say few gases may be there which can break down, right? But the thing is that even the breaking down will require very large amount of strong electric field. You may apply strong electric field, but the passage of charges may not happen. But once if you do this one, electrons are emitted, and because electrons are negative charge, it will get attracted towards the positive terminal. Positive terminal will get attracted, and electron will start moving with a very high speed. And because of this electron moving, there is a spark. That is spark they are talking about. Okay. So this observation was done by her in this this year 1857. Then there were other scientists who also observed something. What was that? In 1888, in 1888, Hallwatch, okay, Hallwatch studied this phenomena further. This phenomena further. Further, he studied about this phenomena, and what he did is he connected zinc plate to an electroscope. He found that zinc plate is illuminated with electroscope. I think you know what is electroscope. Electroscope is a device to measure charge. Okay, so he has taken a zinc plate. Let us take it as a zinc plate. Zinc plate. Okay, and zinc plate is illuminated by ultraviolet rays, UV rays. Okay, then what happens? So this ultraviolet rays, it was found to develop positive charge. Why positive? Because electrons are coming out of the surface. He noted that electrons are coming out and it is developing positive charge. It is developing. How did he discover that this is developing positive charge? He put this or he connect this with a electroscope. Electroscope is a device which is used to you know find out charge, because electroscope or um, gold electroscope have gold leaf. This is a metal sphere, and in the vacuum they have gold leaf like this. Okay? Gold leaf. So if this is having charges, so this gold foil or gold leaf, it is called gold foil or leaf, they start separating because it is developing charges. Okay, positive charges, right? So the idea is that a positively charging plate become more positive charge when it is further illuminated with ultraviolet. So that means if you keep on illuminating more and more ultraviolet rays, it will become more and more positive charge. And how can you see that? By connecting it, you can see that if you keep on illuminating, this leaf gold foil will keep on separating because of repulsion. So that was the observation what he got it. Okay. So he concluded that negative charge particles were emitted from this. So he concluded that negative charge particles are emitted. These negative charge particle is what is we know as electrons. Okay, right. And these electrons which are emitted, they are called photoelectrons. 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 These electrons are the electrons of that metal which get uh, ejected from its surface, right? So this phenomenon is called photoelectric effect. Let us write down the emission of electron, the emission of electron from a metal plate, from a metal plate when illuminated, when illuminated by electromagnetic electromagnetic radiation, electromagnetic radiation of suitable wavelength is called is called photoelectric effect. So what is photoelectric effect? This is the definition of photoelectric effect. So note that suitable radiation has to fall on the suitable means if the energy of the radiation is not sufficient, it cannot eject electrons. That is why the term suitable is used, suitable. So the electromagnetic radiation here we are using in the experiments ultraviolet rays. That ultraviolet rays can produce electrons from the surface. It is ejecting electrons from the surface, right? So definitely the energy of these photons, ultraviolet rays, that must be larger than the threshold, or larger than the work function, you can say. Threshold energy or work function. Okay. Then only it can happen. Otherwise, it will not happen. If you apply some, let us say you apply some visible light, it may not happen. You apply some infrared radiation, it may not happen. Ultraviolet has high energy, so it is able to produce photoelectric effect. Okay. So now we will discuss about this Lennard experimental study, and then we will go into details of that. Right, very important Lennard experimental setup. Lennard Lennard's experiment Lennard's experimental study of photoelectric effect. So Lennard was the first person to study more detail about this. So let us draw the experimental setup. In board exam, it may come. We need to properly draw that. The only thing is that little bit it may look complex, but we need to draw it. So entire chamber is in vacuum, and this side we are calling as C. C means cathode, A means anode. Okay, C is called cathode, A is called anode. So this side, this entire setup is anode. This is cathode. Okay. Now what happens here is the radiations of light is allowed to fall. So this is light, monochromatic light, monochromatic light, single wavelength. Okay. So what happens is that the electrons get ejected out of this surface. And as this electron gets ejected, it will be traveling. So many electrons comes out. These electrons which are coming out of surface will start traveling towards this side. And because of this, there can be current. And note that this entire chamber is vacuum, nothing is there inside. Okay. And this anode is also called collector, and this cathode is also called emitter because it is emitting electrons, photoelectrons. This is a microammeter, so that it is able to measure very small amount of current also. Okay, this device, and this K is a switch here, or S is a switch here. So this switch can be pressed. This is a battery of some voltage, minus plus, right? Like this. How this system works, let us try to understand. And note here that this anode is connected by default with this rheostat from positive side, and this cathode is connected with the switch uh, negative side. Okay, so I think in this graph or in this, suppose if you don't connect battery, let us say it is like this. No, no, I think this circuit is complete. This circuit is complete because suppose this switch is off, then what happens is that your falling radiation electrons may be able to reach and there will be current. Yeah, I think this is connected. This is additional. Maybe we can switch on, then we have to see to this effect. Okay, current. Okay, so let us see what happens here. So monochromatic light is falling here, right? Photoelectrons are emitted. If the energy of radiation is sufficient, then photoelectrons are emitted, right? When and now see how the switch is working. When the switch is open, monochromatic light is made incident from the cathode, then current is measured. Even though applied voltage is zero, current flows in the circuit. Note that, yeah, I think this is what it is. When switch is open, switch is not connected, what in NCRT diagram may be little different. Okay, this is little bit simplified diagram. So when this switch is open and you have applied this, electrons are emitted. Electrons which are emitted have sufficient energy so that it is able to reach here. As soon as electron reaches here, then it goes in this circuit. There is a potential difference and this there is a current. This current is measured from this ammeter. Microammeter means very small current will be there. Okay, then we can measure it like this. Hmm. This photo, so this we are able to measure the current. These photoelectron emitted from cathode moves towards node, but less energetic electrons come to rest before. But some electrons which are very less energy, it is not able to reach here, right? So these electrons, some of electrons having high energy may come here, but some of them may lose, so they are not able to come there. Okay. Now the question is, when we are connecting this switch, then story starts. When anode is given positive, so that's what it is. When we connect this switch, so this anode becomes positive this side, and this becomes negative this side. Comparatively, this becomes negative this side. Okay, right? So when switch is closed, when it is open means here only it can happen. But when switch is closed, then this becomes positive charge. And if becomes positive charge means electrons will get accelerated. That is the idea. To improve the current, we are putting the anode higher voltage, cathode lower voltage. We are giving that externally by connecting a battery. So what is the function of battery? Battery will make the anode positive and cathode negative. So there will be a potential difference. So the electrons which are emitted will get accelerated towards this side. Even though electron will have less energy, still it will accelerate because there is now a electric field. Electric field is created due to this battery. Okay, that's what it is. And now if you increase the potential of this, then we can see more current. If potential is increased, gradually the effect of space charge become negligible at some, and then electron is emitted from the cathode will be able to reach. The current then becomes constant even though voltage increase. This is called saturation photocurrent. This I will explain, very important idea of saturation photocurrent. Okay. First of all, I will explain this experimental setup again to try to understand this experimental setup. So see that the battery is connected, but initially switch is open, switch is not closed. Okay, so if current has to flow, it will not flow through the lower branch having battery because battery is disconnected here. Okay, battery is not connected. You are applying the electromagnetic wave. You are applying some ultraviolet radiation or whatever it is, high energy photons we are applying. So what happens? Electrons are emitted, and as electrons are emitted, they have some kinetic energy. They are able to reach this side, and as soon as they reach here, what will happen? There will be a potential difference developed between cathode and anode, and because of potential difference developed between cathode and anode, in this circuit there will be current. So current will flow in this circuit like this way, right? Remember, current is flowing through this. No, it is not going through the lower branch containing battery because that switch is open. that is not connected at all. That's what will happen. Now you can see the effect of flying more intensity or more different types of wavelength. You can study the effect of that. You can study the effect of that without connecting battery. Note that there is no potential difference initially between cathode and anode. Why? Because you have not connected any battery, right? So how is current then flowing? Current is flowing only when electrons are reaching this end. Electrons, if electrons are able to reach end, then this becomes negative and that becomes positive. That becomes a negative positive because electrons comes out from there. But are the electrons reaching here or not? That is important. If electrons reach here, then cathode becomes positive, this becomes negative, and they are connected by this circuit, so current will flow. That current is called photocurrent. Here we have not applied any battery, so that is one thing we can study. Another thing is that now let us close this switch. Now when you close this switch, what happens? Now when you close this switch, you are making this anode as positive and cathode as negative. Now you are creating a potential difference. So as soon as electrons are emitted here, electrons get accelerated due to the field, due to the electric field between anode and cathode created due to connection of battery. That's a very important point. Okay, so now this we are calling as anode voltage with respect to cathode. We are keeping anode as positive, 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 so that it is attracting the electrons and we can see the current. But this see what happens is that, let us say 100 electrons are emitted. Let us say 100 electrons are emitted and you increase its voltage. So initially all the 100 electrons will not be coming here, so current will be less. But as soon as you are increasing the anode voltage, you will find that 80 electrons are coming, 90 electrons are coming, 100 electrons are coming, so current will gradually increase. But after all the electrons come here, you cannot increase further the amount of electrons because 100 electrons was produced, same 100 electrons are reaching here. After that you cannot increase electron. That current is called saturation current. You have to understand what is saturation current. Saturation current means if 100 electrons are produced and you are increasing this voltage, positive voltage, then gradually all the electrons will be reaching here. So in 1 second 100 electrons are produced, in the same 1 second 100 electrons will reach here. It cannot go beyond 100 because that much is produced only, right? That is called saturation current. Saturation current. So the effect of voltage is there, but effect of this voltage is up to saturation current. After that, if you increase this voltage, it will not increase the current. Very important idea. We will discuss that because there are 4 5 graphs on this where we will be discussing about this concept. Okay. Basic idea that what are we measuring? We are measuring current here. We are measuring current also. So that current is only we are going to see. How current changes when you change the electromagnetic waves. Let's say you put infrared, you put ultraviolet, you put violet, you put green light, whatever. So effect of different wavelength on current you can study. You can study effect of different anode voltage on current you can study. You can study effect of different cathode plate on photo currents. So these are the things we are going to study. This is the fundamental of this. Okay, so now let us study this already experiment I discussed. Now let us study the graphs. Okay, let us study the graphs. Now I am going directly into the graph. Anything else is there, it will come. We will be discussing. So 4 5 graphs are there. Let us go into the graph. So the first graph is about the photocurrent versus intensity. Okay, photocurrent versus intensity, that is the graph. Or I think this graph is first photocurrent versus anode voltage. Yes, photocurrent versus anode voltage. Graph number 1. Photocurrent, photocurrent versus anode voltage. Anode voltage. Okay, so this graph, if I draw photocurrent, I am going to call it as IP. IP means photocurrent, and this is anode voltage. Anode voltage. So what happens? This graph looks like this. This graph starts from a point here, which is a negative voltage, which is called stopping voltage, and this graph goes like a non-linear graph. This graph goes like a non-linear graph, and then after that it attains a maximum value. Now try to understand why this graph and this value, what it attains after some time. This is what we are calling as saturation photocurrent, ISAT. ISAT means saturation photocurrent. Saturation photocurrent. Vs is called here stopping voltage. Stopping voltage. Okay. Let's try to first understand this graph is a very significant graph. Okay, what happens in this graph? Try to understand. So we have cathode and anode. Cathode is where electrons are emitted. Anode is where you are applying voltage, right? So when we are saying the voltage of anode, it is the voltage of anode with respect to cathode. Okay. So suppose this is cathode, and this is anode. This is cathode, this is anode, and here you are applying the electromagnetic waves. So let us say ultraviolet rays you are applying. Okay, whatever rays you want, you apply. So electrons are emitted here. These electrons are emitted, and these electrons goes this side towards the towards the anode. Suppose here, what is meant by negative? Let us try to understand. So relative to cathode, let us take cathode as 0 voltage. Okay, assume cathode as 0 voltage. Anode voltage is, let us say, negative. So electrons which are negative will get repelled from anode, right? Electron will be getting repelled. Why? Because electron is negative charge, it will not go to the negative anode. So that is what it is showing first. Suppose if you apply negative, 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 then at one negative voltage, electrons are not able to reach the anode. That is what the important point. Electrons are just missing to hit the anode. Why missing? Because electron has energy. When electrons comes out of the metal surface, it has energy, and because of that kinetic energy, it is rushing towards the anode. But anode is trying to repel it. Anode says, "Hey, don't come, don't come, don't come," because it is applying a negative voltage. So because of that negative voltage, one particular negative voltage, that is called stopping voltage, it is just stopping before reaching anode. It's not that it is not traveling, it is traveling, but the poor electrons cannot enter into the anode. That voltage of anode is called stopping voltage. Clear? Yes, that is what it is. But now, oh, some problem is there. Okay, no problem. You can hear me, right? Clearly? Okay. So what happens now? Suppose I increase the voltage. Now I will make less negative, less negative, less negative. So what we see, that electrons are having some energy. Electrons are able to strike the anode voltage. Even when you keep anode voltage 0, you see, even when anode voltage is 0, still there is some current. This current is solely because of electron is so powerful. Electron has got energy, so it is rushing, 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 and it is hitting that. So this energy is only because electron has got energy. Now, if you increase voltage, means you are trying to make anode positive. So if you are making anode positive, you are inviting the electrons, right? You are, because electrons will get attracted then. So then definitely electrons will be coming more, and then current will increase. But the idea why current is increasing, because of this region. Suppose there are 100 electrons are produced. Initially, all the 100 electrons may not be able to reach there in the same time. So that is the reason current increases, and once all the 100 electrons are able to reach here, it will achieve a saturation current. This is the saturation current. Clear? So now let us try to understand. This is a very deep concept here. That suppose if I say that n number of electrons, and let us say n1 number, or let us say n1 photons are falling, n1 photons, and due to n1 photons, note that same n1 electrons will be produced. Okay, so suppose if you apply n1 photons per second, we are talking of per second. Okay, per second. So in 1 second, n1 number of photons are falling, and in that same 1 second, n1 number of electrons emit per second. Per second. Now these n1 electrons are able to reach there or not, that is the question. Let us say here n2 number of electrons are reaching, n2 number of electrons per second, they reach anode. So you know what will be the current of anode? Current, what we are telling as photocurrent. This photocurrent will be n2 into E by time. Time is of course 1 second, you can say, because you know in 1 second that many electrons are reaching. So current is charge by time. Total charge is number of electrons into E charge divided by time. Time is 1 second. So that is the photocurrent. But the thing is that if you increase the anode voltage, this N2 will increase, and finally N2 becomes equal to N1. This is what is called saturation. Saturation. So then in the saturated photocurrent will be N1 into E by time. Time is of course 1 second, because we are talking of per second. So per second time is 1 here. Okay, 1. So this will be the saturation, and once saturation happen, after that even if you apply for more positive, current does not change. So this graph should be first clear. Are you clear about this? Yes. Let us go to the next graph. Now we will discuss about the photocurrent with intensity. Second graph number 2. We are talking of saturation photocurrent now. Saturation photocurrent versus intensity of light. How will this graph look like? This is saturation photocurrent versus um, intensity. Intensity. So this saturation photocurrent, all other things are kept constant. Okay, so this graph is going to be straight line first of all, and why this graph is straight line, that also I will prove, although it will not be given in the book, but let us understand that. So what is this saturation photocurrent? Just now we have seen saturation photocurrent is all the electrons uh, which are being produced into the charge divided by time. Of course, time we can take as 1 second. This is what it is. Now, what is the intensity? What is this intensity of light? What is intensity of light means? Yesterday also we discussed what is intensity of light. Suppose if I say intensity of light in terms of energy, so N into E, total energy by time, area also coming, right? So now let us take the ratio of this. If we are talking about light intensity, we can take, or otherwise if you talk about the photon intensity, that also we can take. But generally, if you remember, we discussed this as photon intensity only, and photon intensity concept is number of electrons, number of photons per unit time per unit area. So the better definition of this will be according to syllabus of this course of NEET syllabus or JEE syllabus. We define intensity as the intensity of photon, not the intensity of light. But some people may argue that it is the intensity of light. That argument has to be properly understood what he means. You have to ask that person what they want. Okay, so because I have seen many people arguing about this, but in the textbook they have given this year also in the NEET, re-NEET also one question came where exactly this is what the definition they are using. If you go by this definition, you will be in problems. Okay, so you have to be careful. Right, so now you see the ratio. Let us take the ratio I saturation by I photon intensity. So N1 into E by T, here N1 into TA. So N1 TT will get cancelled. We can clearly see that intensity of saturated photocurrent is equal to this area will come here, right? Area and into E will come here, and this will be intensity of photon. So definitely this is anyway constant, so we can clearly see that saturation photocurrent is equal proportional to intensity of photon. That's why you can clearly see that this is a straight line graph. This calculation explains why this graph is a straight line. Clear? Okay, then let us go to the next graph, which is the photocurrent versus the voltage. Photocurrent versus voltage. I think the same graph is we have already seen that, but we can see the effect of intensity. Effect of intensity. Third graph, photocurrent, I photo that versus intensity. Intensity means intensity of photon only. We are talking of photon intensity. So now suppose here we will take, remember this should not confuse because there is only L is here. I photo, I photon. So we should be clear about this. So we are telling here this is voltage. Uh, sorry, photon versus anode voltage. It's anode voltage. So this is I photo. So already we discussed about this, that this graph will start from a stopping voltage, which will be of course negative. So this graph will go like this, like this, like this, and it will attain saturated. Now this graph, I am going to study the effect of intensity. Let us study the effect of intensity. Effect of which intensity? Photon intensity. Photon intensity we want to see. Suppose I increase the photon, then this graph will be going like this, but it will attain a higher value of photon. And now if I increase furthermore, this will go, but they will all be starting from the same point. That is what is an important point to note. So suppose this is the intensity of photon, or let me write this just I1. I1 intensity, this is I2 intensity, and this is I3 intensity. So here we should note that this intensity I3 is larger than I2 is larger than I1. So in this graph we can see the effect of intensity. That means suppose you are applying more photons, more electrons will be produced, and the saturation current will increase. Suppose instead of 100 photons hitting the cathode, now let us say 200 photons are hitting. So 200 electrons will be produced. Because of this, current will increase. That's how this graph is becoming saturated, but current saturation level is increasing. That is the reason for that. Okay, so that's the effect. But note that this remains same. Why? Because we are using the same. This we will study further. Stopping voltage will depend only on the frequency of that. Okay? Frequency of radiation we are not changing here. That's what it is. Okay. Now we'll see effect of frequency in this graph. Same graph, but now we'll see the effect of frequency in this graph. Let us keep the same graph, but study the effect of frequency. So the I photo current, and this is anode voltage, and now suppose we have this is minus Vs1 minus Vs2 minus Vs3 minus Vs3, three stopping voltage. And here let us take this graph first, this graph, and this is coming like this. Then this graph, this will be also coming, but it is now coming to the same line. The third graph is coming to the same line. Okay. So here now you see for each of them, this particular saturation intensity is the same, but their frequencies are different. Okay. So here notice the effect of frequency. Effect of frequency. Effect of frequency. So here in this first case, you can say the frequency was used as F1 frequency was used. F1. In this case, frequency F2 was used, and this case frequency F3 was used. Okay. So we can see that effect of frequency, third frequency is larger than second frequency, larger than first frequency. But note that the intensity of the photon is kept as constant. Photon intensity is kept as same for each of these stuff. What is changing is we are changing the wavelength or frequency of the radiation. That's what we are doing. And we can see that if you have larger frequency, you have larger stopping voltage. Stopping voltage 3 is larger than stopping voltage 2 is larger than stopping voltage 1. Okay, that's what it is. So this graph is also important graph. Then last graph is the stopping voltage versus frequency. That is what is Einstein's photoelectric equation that we will see. So let us note that graph. Einstein photoelectric equation. Photoelectric equation. What happens in Einstein photoelectric equation is Einstein say that this cathode is there, and this radiations are hitting. Radiations means these are photons. Photons. Photons are hitting, and electrons are coming out of this surface. And electrons are coming out with some kinetic energy. Obviously, it will have kinetic energy. Photons energy is of course then energy of each photon is h into frequency that we have already discussed, or hc by lambda is also we can write. This is energy of photon, and this metal or this material, this particularly metal only, this metal has some work function which is phi. So this metal will first check whether the photon has energy larger than or not. Okay. If the energy of the photon, each single, note that it will check only single electrons. It's not like you can suppose one photon has, let us say, let us take example, the work function is 10 electron volt. Okay, 10 electron volt. That means if the photon energies should be larger than 10 electron volt, then only electrons will come out. But suppose one photon has 5 electron volt, and another, all photon will have same energy, right? Because same radiation it is. It is not that three photons can hit and electrons will come out. No, even if millions of photons will hit, it will not come out, because the idea of this photoelectric effect is based on single photon absorption theory. Single photon, single photon absorption, absorption theory. Single photon absorption theory is a major idea behind photoelectric effect, which Einstein identified. But nowadays, in recent time, when I taken one course in the engineering design department in IIT Chennai during my semester courses. So that time I taken laser, and this laser was the main course. So that time this the HOD, the department, Vasa sir, his name is, very nice person, very humble person, very I if in IIT, if I like one person, that is that person, Vasa sir. So he explained that now the research is going on and things are changing. So they are developing also multi-photon absorption theory. That means many photons can be absorbed, and even energies of photons are less, but more photon can give more energy. So there can be electrons emission happen. But we don't know, still it is not in our syllabus here, but in research it might be possible. But photoelectric effect which was given, it was given for this single photon absorption theory. That means if the energy of a single photon is larger than work function, then only photoelectric effect will happen. Okay, so that is the idea behind it. So if the energy of the photon is larger than work function, then photoelectric effect is happening or is occurring. Otherwise, it is not. Electron may be produced. Let us say you say electron can come out, but in order to come out also it requires energy, right? You cannot just eject it. After getting ejected, it has to travel. So that means it should have some energy. So that is why, according to Einstein theory, says that the kinetic energy of this electron will be equal to the remaining energy. So E is larger than this. So E you have already given, and phi it is absorbed by the surface. So this is the remaining energy which will come out as kinetic energy of the electrons. But note that electrons may lose energy due to collision. So that is why Einstein is saying that this is the maximum energy of electron, maximum kinetic energy of electrons with which it will come out. Okay, that is what the theory is. Then we can now think about it. Suppose for example, from this cathode, electrons has come out. Electrons has come out with a kinetic energy, and this is anode. And let us say you want to stop it, so you started applying a negative voltage here. So because of negative voltage, electron will feel repulsion, and let us say that electrons still travel, but it is not able to enter, and electron stops just before reaching anode. It stops here. So the work done is change of kinetic energy when we apply. Then this kinetic energy maximum, we are talking of this maximum kinetic energy, this is charged into the potential difference. So this charge is E, and stopping voltage is here. So this is what it is. Okay, so this is the kinetic energy maximum. So if we substitute here, we can get some equation from here. So E into Vs is equal to energy of photon minus work function. So now we can write this energy as h into frequency minus work function is E into Vs. So from here the stopping voltage formula that we will get as h by E into frequency minus phi by E. This is the equation which we are going to plot now as a graph. So let us plot this as a graph. So suppose I am plotting this as a frequency and this as a stopping voltage y. stopping voltage. Okay, frequency. So if you see here that when you consider frequency 0, then stopping voltage will be negative here minus 5 by 8. So there will be straight line which you can try to draw like beyond this. So solid straight line we will keep here, okay, like this, but this is dotted. So what it means here that this frequency, right, where it becomes 0, that frequency is called the threshold frequency. This frequency is called threshold. Okay, threshold. So let us note what is threshold. So if stopping voltage is 0, this will be threshold frequency, and this threshold frequency, that means if this becomes 0, so this is based on the energy of photon greater than 5. Okay, or let us say you can equate it. Hmm. So if you consider that it is just ejected, then it is the case when it is just emitted with kinetic energy maximum as 0. So in that case, kinetic energy maximum is 0 means we can say that hc by h into frequency, this frequency is called threshold frequency, is equal to 5. So from here this threshold frequency can be calculated. Threshold frequency can be calculated as work function by h. So that's what the frequency must be larger than threshold frequency for photoelectric effect. For photoelectric effect, the frequency must be larger. Similarly, we can convert them into wavelength also, because energy has to be, let us say this is the minimum energy. So it we can write as C by lambda also and phi. So we can say that lambda is equal to lambda is equal to hc by phi. Hc by phi. So the wavelength must be, this is called the threshold wavelength. Threshold wavelength. So wavelength must be lesser than threshold wavelength for photoelectric effect to happen. Photoelectric effect to happen. Okay. So this is all. This is the total thing about photoelectric effect. I think we have done a good work. We have completed this topic, photoelectric effect. So that's all. I think this is the major topic of this chapter, photoelectric effect. And if you are done with this chapter, then most of the things are done now. Then you can work out. Lot of questions will be there in this chapter. Okay. Then anything else will be there. I think beside this, already we have done Davidson German experiment is there also in NCRT. Let us quickly cover that. Okay. 10 minutes it will take. After that, this chapter is over. Okay. Davidson German experiment. Hmm. Yes. 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 Yeah. Yeah. That's what it is. Ah, what decreases? Hmm. Hmm. No, yesterday what we discussed? We discussed that uh, both decreases. I think we discussed. Ah, yes. Yes. Hmm. Hmm. How? Hmm. Simply saying it is not sufficient. What? Which formula? No, 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 no. Simply saying it is not. Suppose if I say something, I have to tell now from which source I tell. If you say better not in syllabus, that is better, right? That is better not in syllabus, don't say that. But if you are saying that, well, then you need to explain things. I will check, I don't know, but I told what is based on slit, based on the single slit we told. But pinhole, I will check about it. What is the theory behind it? I don't know, because that is not in syllabus. But what? Hmm. No, no, no. Means it's said like that means it is not like this. It is the thing. Idea is that why it is like this. We need to ask really. If really if you are interested, then we have to ask. Then we need to check that. Then means we need to also check different books. What is the theory behind pinhole and how diffraction happens in that. Of course, pinhole is a circular aperture. In circular aperture, how diffraction pattern takes place. But in NCRT, that 1.22, that is the only formula that they have given for circular aperture, right? Yeah. Hmm. So let me check if anything is there. Hmm. What did he give? Any formula or any idea did they give? No, no. Now I'll give the proper answer. This is a pinhole and this is a string. Pinhole. Pinhole means it is a circular aperture, circular aperture. Okay. Now let us say that this is the diameter of this. Okay. This is diameter. Consider diffraction pattern obtained from sunlight incident on a pinhole of diameter. How much is the diameter B? B is 0.1 micrometer. So, and what is the wavelength of light? How much nanometer it will come? Let us check that. This comes 10 to the power minus 7 nanometer. So, correct, 10 to the power minus, no, sorry, 10 to the power minus 7 meter it will be. So, 1 nanometer it will be, right? Okay, this will be 10 to the power minus 7 meter. This is like 1 nanometer, correct? This diameter is 1 nanometer. Now, if you are taking white light from sun, white light from sun, then white light is, uh, yeah, then it will be 100, I think, sorry, correct, na? Then it is better now. Now we can definitely check out details. So 10 to the power minus means 100 nanometer it is. So then it is comparable to wavelength, because wavelength of light here, white light wavelength is from 400 to 700 nanometer. Now tell me, diffraction happens or not? Diffraction will happen because this is almost wavelength is 4 times. So comparable this it is, right? The aperture size is comparable, so diffraction pattern will happen. Okay, now so they are saying that if the diameter of pinhole slightly increase, not much increase, slightly increase, so it is still comparable. We are assuming that still diffraction is happening. It will affect the diffraction pattern such that its size decreases. Size means I am talking about the central bright fringe, okay, central bright fringe, and intensity. So effect on central bright fringe, minimas and other things you leave it, secondary maximum leave. So this is the central bright fringe. Central bright fringe will be forming here. So this radius of central bright fringe. Now I will write the formula for radius, because it's a circular aperture. That formula according to NCRT, this radius of this R naught, radius of this is 1.22 lambda d by b. Here this is the distance capital D, and this is lambda 1. If you take slit, now then slit means lambda d by b only come. One factor will come, 1.22 will not come. Okay, but 1.22 comes due to circular aperture of this, right? Now if you see this side, slightly you are increasing, b you are increasing, so as you increase b, this is going to decrease. Okay, so this size will decrease, that is definitely correct, right? Size will decrease, that is definitely correct. But what about the intensity? Intensities of what? Which intensity are we talking about? We are talking about the intensity of this maximus. Yes. No, 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 that is definitely not correct. That is wrong. Okay. So this R naught, this size of this, because B you are increasing now, you are slightly increasing, right? So when you are increasing this, then R naught should be decreasing. So size will decrease. Okay, size will decrease. What about intensity? Hmm. Size will decrease. Hmm. No, no, that is not correct. So size will decrease for pinhole, and then what happens is that what about this? Um, what about this intensity? So intensity we discussed now, it is also inversely proportional to that. So intensity, what we discussed, intensity is decreasing or increasing. This formula for intensity, if you remember, I naught sine square, sorry, this was sine uh, n delta phi by 2 by n delta phi by 2. But this formula is for slit. This may not be applicable here, but let us apply this formula. So according to this formula, if you remember, delta phi was uh, b by n sine 2 pi by lambda was also there. So 2 pi by lambda into b by n sine theta was there, right? So if you substitute, so from n delta phi by 2 factor if you take, then it will become pi b by lambda, pi b by lambda into sine theta. So in the denominator this b will come, and if it is increasing, so b is increasing, intensity will be decreasing. Intensity also will be decreasing if you are slightly changing it. That's what the result is. But let me check about more about this white light diffraction. Brightness at the center, image intensity. For an extended source like sun, each point on the image receives light from corresponding bundle of rays. As pinhole diameter increases, light intensity. The blood spot area, so the intensity, approximately constant it is saying. Intensity does not change, merely it is independent. Hmm. But if you consider smaller pinholes cause noise, reducing the peak intensity, this is making the image to a small pinhole causes more splitting, reducing the peak intensity. Diffraction is this. In this regime, making the whole diameter smaller actually makes the image dimmer and blurry. Hmm. It is saying that intensity is increasing. If you increase slightly, that intensity increases. This it is shown. But that is not given how. Okay. But one thing they are making this assumption that the wavefront which is coming here, this area will be increasing. Exposed area of the wavefront will increase. So more secondary wavelets will be produced, and more secondary wavelets produced means it will be producing more intensity. So I think that formula is only for single slit, but this is a circular aperture, so we can say intensity will increase. Intensity increases, but what is the formula that we don't have? We cannot derive it right now. It will require more analysis for that. Okay. So here they are saying that if you are increasing this size aperture, then more waves will be reaching, and more size of wavefront will increase, more exposure will happen, and intensity will increase. Okay, that's what it is saying. So according to this, the intensity should increase, but the size should decrease. Okay, that is the answer. Yeah. Let me once more check with another source. Size decreases, intensity increases. That is what is the answer given. Okay. So the final answer of this is intensity increases and size decreases. Okay. Size decreases. This is the final answer. Now you can check it from anywhere. Check it means not just Google it. You have to check with some good sources. Okay. So the intensity will increase. The increase of intensity can be explained by the increase of this aperture size of the wavefront. More wavefront is exposed, so more intensity will happen. But that formula for intensity is not going to work because this is for single slit. Okay, single slit we do not have any formula. Means single slit we have, but we cannot apply that single slit formula here because this is a circular aperture. Note here that this formula, why are we applying? Because this formula is for circular aperture given in NCERT. Okay, this we can apply. Definitely this formula we can apply, and this reasoning is correct because based on this formula, we can say that if you increase P, it will decrease. But intensity we cannot say. So for intensity, the reason is that more exposure size will happen. As more exposure happen, more rays will be coming there. So more intensity will be increasing. That is just the explanation. No mathematical equation is there. Got it? Hmm. Hmm. Okay. But also one important thing is that for an object such as sun, extended object such as sun, intensity will not change much. Okay. If suppose one other option is given that intensity does not get affected, we can also choose that. Intensity does not get affected for note intensity does not get affected for extended object like sun. Okay. So actual answer should be this one. Intensity should not get affected. Okay. So last topic, let's finish this. Davidson and German experiment. Davidson and German experiment. Davidson and German experiment. Okay. So this experiment it establishes the wave nature wave nature of electrons. It establishes the wave nature of electrons. Okay, electron is a particle, but using this experiment first time in the history in 1927. Okay, this happened in 1927. They proved that electron has, they were American physicists. Okay, okay. So how did they do? Right? They measured actually de Broglie wavelength. So they measured they measured de Broglie wavelength, de Broglie wavelength, de Broglie wavelength for de Broglie wavelength associated with electron, and experimentally verified it using electron diffraction. Okay, so what happens in electron diffraction? Let us try to know. So there is a experimental setup I will draw. So there will be some filament like this. This is called electron gun. Electron gun. It will be ejecting electrons at very high speed. Okay, and there will be a target like this. This is target is some nickel target will be there. Nickel crystal, and this gun is emitting this, and these electrons are going away here. Here we will be keeping one detector. Detector, and this incident electron. This is an incident beam. Incident beam of electrons. This is diffracted beam. Diffracted beam of electrons. Okay, and let us say that here is making with this surface theta angle, and this angle is angle phi. Okay, so there is a detector, it will be able to detect that. Okay, so let us note here what happens. So this is a nickel crystal. As this incident beam falls, it will strike and it will get reflected. So now what happens, the detector can move over this. Detector can move and try to detect where the intensity of electrons is more, right? So at a particular angle of theta or a particular angle of phi, this detector is capturing the maximum amount of reflected electrons. That means somewhere it is maxima, somewhere it is minima. So that means what? It is behaving like a wave, right? So, so somewhere the intensity of electron after hitting the crystal, somewhere it is looking maxima, somewhere it is looking minima. So we can find out some place and we can find out the angle. Okay, so some technical details are that we should note here, like what are the values of these angles are there where they find maximas. Okay, so they are measuring this as 50 degree, and they are saying that this 50 degree, and they are using an accelerating voltage of 54 volt they are using, right? Yeah, so 50 degree 54 volt, this is an important experimental thing. And then how are they measuring this? So that is what we need to note here is, let's note here that these are the layers of atoms of the nickel. Let us say this is nickel atoms like this, and these rays are coming. For example, this ray is coming and it is coming like this. So this angle is theta, and this is phi. And another ray also will be coming here and it will be coming like this way. Okay. So we want to find out this interatomic distances is d, right? So here also let us try to calculate the path difference here. This angle will be theta, this will be total angle phi. We can try to calculate, right? This is perpendicular, so this will be also theta. So this length is d here, this length is d. So this will become d sine theta. Similarly, here also, if I take this is also d sine theta. So this 2d sine theta is nothing but the path difference, and we can take as n lambda 2d sine theta. We can take n lambda for maxima, and then we can apply to do the calculations, right? So now if you try to find out how much that happens, let us try to do that, and let us take n is equal to 1 for first maxima. So 2d sine theta becomes lambda. Okay, but now how do we calculate from here? D is given. Okay, so note that D for nickel crystal, this D is 0.91 angstrom. That is already we are knowing for nickel interatomic distances. Okay, and here note that the sum of this total angle to theta plus phi is going to be 180 degree. Okay, from this straight line. So if I substitute here the value of phi, they have calculated 50 degree. So 2 theta plus 50 degree becomes 180 degree. So 2 theta becomes equal to 130 degree. So theta becomes equal to 65 degree. Right. So let us now substitute. So 2 into D is what? 0.91 angstrom. Angstrom means 10 to the power minus 10 sine of 65 degree. That will give us the wavelength, right? This wavelength was calculated by Davison and German as nearly 1.65 angstrom. This wavelength he calculated, right? After he calculated this wavelength, what did he do? He tried to calculate also the de Broglie wavelength. Remember, for electron yesterday we have studied the de Broglie equation 12.27. Remember, root under voltage. Do you remember, Sam? First we just written that, right? So this formula he had tried to calculate de Broglie wavelength. Note that this is de Broglie wavelength. So from here he got very much surprised by doing this calculation. 12.27 by root under this voltage was 54. Now when he calculated, he is getting 1.66 angstrom. That was a surprise. That he matched. He was successfully able to match the wavelength due to the wave and this wavelength due to the de Broglie equation. That was the success of his experiment. Okay, right? So with this idea, we can establish that electron behave as a wave. And that's the end of this chapter. I think we have completed everything related to this chapter. Okay, so now you can work out questions on this chapter, any type of questions on this. So I think one class we can solve problems and then we can go for other topics like atoms and nucleus. Okay, fine. Any doubts you have? Okay, then we'll see next class. Okay, bye bye. Sam, good night.